Okay, so today we are first considering the case of field orbitals. Now when I am saying field orbitals, which nuclei have field orbitals? I mean all the levels are filled up. They we know are known as magic nuclei. And what are magic nuclei? Nuclei whose either Z or N, that is either total number of protons or total number of neutrons there or magic number. Okay, either of them. And if we have both of them together magic number, then it is known as doubly closed shell nuclei, DCSN. Okay, so now you see, we will consider any nucleus as we will consider it as a magic nucleus plus a few particles or holes. Let me clarify. Say for example the 18 oxygen, famous example over here. Now we can consider it as a 16 oxygen plus 2 neutrons. This is a much better way of understanding the structure. Okay. Similarly, what about 14 oxygen? Here you see 6 neutrons. So I can consider again this as 16 oxygen plus 2 neutron holes. Okay, here 2 neutron particles you can see, and here 2 neutron holes. So now what about the field orbitals? Let us consider one such level. Say this orbital 1p3 half. This is filled. Here you see 4 either protons or neutrons are there. Now what is the m value of each of them? Minus 3 half, minus half, plus 3 half. So what is the total m? Total m, if you add up, it will be 0. So in fact all field orbitals, their total m equal to 0. Right? Now I am actually, what I want to do is I want to find the total j value. What is the total j for field orbitals? This is what I want to do. Now let's first write down the wave function for this state, for this orbital. Okay, so you can see this is the total wave function over here. Now I will try to use certain relations and find correlation in this wave function. Okay, so now in the psi NLJ wave function, which we wrote down as a Slater determinant, for each term we will have this term, this relationship, and also the address symmetry of psi NLJ will mean that for each I, this j plus minus into for I psi NLJ equal to 0. This means that you cannot take it, either jump it to above state or below state for each of them, and this will mean that overall j plus minus into psi NLJ will be equal to 0. Now if we use both these conditions together, then we know this expression for j operator, j square operator, written in terms of j plus minus plus jz square. So if we use this information in the wave function, we will get j equal to 0 and m equal to 0. Now what about the parity? Parity, we know it is written as this into 2j plus 1. Now the states are all filled, so this means that 2j plus 1 is even. See our example of 1p3 half. There j is equal to 3 by 2. So what is 2j plus 1? 4. So this means that the overall parity will be always positive, and so all field states will have j pi equal to 0 plus. Okay. Okay, after the case for field orbitals, that means, say for example, here previously we considered the case of 16 oxygen, right? Previously we considered the case of 16 oxygen. What is this? This is a doubly closed shell nucleus, DCSN. Why? Because both proton and neutron numbers are magic. And using the arguments of the previous case, we saw that all the orbitals are filled, so the total, the ground state spin parity will be what? J pi equal to 0 plus. Fine. Now let us add one more nucleon. So the situation will be like this: all filled orbitals plus a single orbital unfilled which has got only one particle. And what will be the case? So we will now consider the case of 17 oxygen. Say, so 17 oxygen equal to this filled orbital, this is 16 oxygen plus the unfilled single neutron. Now let's do the analysis. So single particle in orbital NLJ, generalized case. So the Jz, now we have got single particle, so only one index. So Jz operator acting on phi NLJ will just give m into phi NLJ, m, right? Again J square operator acting on this wave function will give j into j plus 1 wave function. Fine. Now let's talk about the total angular momentum, I mean the total angular momentum of this system entire. So total, let's first write down the total z component of angular momentum, Jz total. What will it be? It will be Jz of the filled orbitals plus Jz of this. Now we already know that Jz of this filled orbitals is 0. So it will be just the value of this. So J. You see, it will be 0 plus Jz, so it will be just Jz. Next, what is the value of J total whole square? So A plus B whole square, if I write like this, so Jz, J filled whole square plus 2 J filled dot J. Now this is all 0, these terms. So these two terms will be 0. So this term will be equal to just J square, this one. Now if we use all these arguments, we see that the total J is equal to just the small j of the last unfilled particle, right? And also whatever the parity, parity is that of the last unfilled. So it is this particle which will govern the parity as well as angular momentum for the ground state of this nucleus, which has got a single particle in an unfilled level. Okay. Now again you must consider that all this analysis, in all of them there is no residual interaction, nothing. Okay, so now let us consider a hole, a single hole in an orbital. Okay, say for example this 15 oxygen, 8, 7. So if I am considering the neutrons, so the last unpaired nucleon will be in 1p half, and this I can consider as 16 oxygen plus one hole over here. Okay, now how we do the analysis? So for that, let us designate phi minus 1 as the system with all levels filled except n, l, j, m. Again generalized case I am considering. So in this case I can write down the Jz operator acting on phi minus 1, so it will give me minus 1, minus m, and again j square, it will just give me j into j plus 1. Okay, remember minus m, this is due to the fact that we are having a hole. For a particle it will be plus m, hole minus m, and since we can couple this phi minus 1 and phi jm, so we will get j equal to this we can write as, we can couple this to j equal to 0. Okay, so now we have considered till now what? Only one particle or only one hole above the filled level, right? Now we will consider two particles. Okay, so as I was saying, we will now consider two particles in an orbital. So again the situation, let us consider an example over here. See, 18 oxygen, which you can consider as a 16 oxygen core plus 2 unfilled nucleons, and in this case these are 2 neutrons, right? So since we have got two particles, let us write down the individual quantum numbers NLJM, NLJM prime. So the total wave function, this I can write it as j square mm prime. Now I have written here as a Slater determinant, and of course since I have written here as Slater determinant, so this means from here you see this will have a property like this. If we switch the m and m prime. The negative sign will be picked up over here. Now we will use these two relations to form a state of good angular momentum or total angular momentum J. Okay, so this means that J plus J, these two are different m and m prime, they will form a total angular momentum J. Okay, so I have written this as a what? Coefficient. Now we will talk about Slip's-Gordon coefficient. This you have done in your addition of angular momentum class. Okay? Atomic physics. Okay, so now let us use the symmetry property of Slip's-Gordon coefficient. So what I am going to do is I am going to do some mathematical jugglery. I will do some operations and then I will come back to the same old stuff and then I will try to equate the two of them. We have been doing this for a long time. Say for example integration by parts. There also some part is left over, some integration is left, then again it comes back and we get a result. So here if you use the symmetry property of the Slip's-Gordon coefficient, so this is my total good wave function with good angular momentum. So I can write it as minus 2j minus j. Now look over here as this. This I am using the symmetry property of Slip's-Gordon coefficient. Now here what I am going to do, I am going to, here you see the ordering is different. So if I change this ordering, previously I wrote down an expression where if you change the ordering you will pick a minus sign. So here I am picking up one more minus sign. Right. Now you see this expression and this expression, they are both the same. However, there is plus 1 over here and we have got this term. So this means that this entire term should be plus 1. So I have written it over here. So this means that this term should be even. Otherwise, minus to the power even, only then you will get a plus 1. So this means that this entire term is even. Now we are talking about 2j plus 1 and 2j plus 1 is always what? Even. You consider any half integral value. So this is even and this is even. So you get from all this analysis, the result is that J will be even. So if we consider two particles in an orbital, the total angular momentum will be even. Okay, so this is our takeaway from this entire set of calculations. And this we have done after using the total wave function written in the form of Slater determinant. Later on we made a state with good angular momentum, then used the symmetry properties of Slip's-Gordon coefficient, then equated the two terms and then we obtained this result. You remember this is very important. So the question is, show that for two orbitals, for two particles in an orbital, the total angular momentum is even. So if I ask you that, you will have to show this calculation. Now again, this set of calculations can be avoided and this thing can be shown much simpler way using M-scheme calculation. It's a geometric way of doing stuff, just addition, subtraction, but this is much more complete, much more generalized. So anyway, one important correction. So you see here Jm, right? Jm ordering is M prime. Okay, here ordering is mm prime. Remember. Now when I am using the symmetry property, here you see the ordering changes. Ordering is m prime m over here, m prime m, right? When I am using the symmetry property, m prime m, and this term is over there. Next, now I am using this property of conversion from m prime to m prime m. While doing this, you pick a negative sign. So if I am going to m prime m to prime over here, see prime. Here m prime m, here prime. So I will pick a negative term. So it is over here. Okay? So this is the clarification. Okay, so now particle whole combination. Right. So don't be afraid, I am not going to show you any more calculations. Let's instead consider some example. Say for example 40 potassium. So potassium has Z is equal to 90, N is equal to 21. So I can write it, let us try to write it in terms of 40 calcium, which is a doubly closed shell nucleus, right? DCSL. So I can write it as 40 calcium 20 20. So 19 is 20 minus 1. So 1 proton hole, and 21 is 20 plus 1. So 1 neutron particle. So this is 40 calcium plus proton hole, neutron particle. And this proton hole is in D3 half. And this neutron particle is in F7 half. Now this we write it down in this way symbolically. So this is pi for proton, D3 half minus 1 for hole, and here we don't write plus 1, we write just like this, nu for neutron, F7 half. This means it is already 1. So 1 neutron in F7 half and 1 hole, proton hole in D3 half. Okay, so what's the total angular momentum? 7 by 2 minus 3 by 2 to 7 by 2 plus 3 by 2. This is, you will get 5, 4, 3, 2. Okay, what's the parity? Parity is you multiply the two proton neutron particle proton hole. Parity is minus to the power L, right? So for hole it will be D. D is L is equal to 2. So minus to the power 2, and for F it is 3 minus to the power 3. Overall you will get a minus sign. So the total spin parity will be what? 2 minus 3 minus 4 minus 5 minus. Okay. So I will give such similar examples. I will give in the examination. You have to show me this configuration and what's the value of total spin parity. Right? Okay, so now we will solve with all these discussions. After them, we will now solve the 0p shell model, which is the simplest shell model. So in this case, we have got an inert 4 helium core plus 2 single particle states to fill. Fine. So let me write down the total Hamiltonian again. H0 plus summation half to avoid double counting. Bolo. And we will have to solve this. Okay. I have already talked about this. So this is the total Hamiltonian, but difficult to solve due to its presence. And we will treat this using perturbation theory. And so we will solve this over here, where this H0 is, you see, I have already included the single body potential, one body operator, and this is equal to either your Wood section or harmonic oscillator plus L dot S, and L dot S interaction I have included. Okay, so now let us separate and solve the single particle problem. So P plus U, phi alpha, E alpha, phi alpha, right? I am separating, and later on I will use the residue. I will use perturbation to treat the residual part. Okay. Now what is alpha over here? Alpha is just NLJM with L equal to 1, N equal to 0. Why? Because we are considering the 0p shell. Now look over here. What are the values of J? J is equal to L plus minus half. So here we have only two values, half and 3 by 2. And you must also remember that since U is scalar, so this means that because of rotational invariance there will be M degeneracy, and as a result we will have two eigenvalues. E 3 by 2 and E half, corresponding to J 3 by 2 and J equal to half. Now here I have written down all the allowed values, right? Their quantum numbers here, and this is the total isospeed value and this is the total angular momentum. I have written it over here. You do check it whether you really get this or not. Okay, this is important because in the examination I can ask you that for this two body problem, zero P shell, write down, calculate and write down the allowed states. What is the total T isospeed and total J? So you have to do this. I have written here, you have to check this yourself. Okay? And this we will use now for the perturbation treatment for residual interaction. Okay, so these are the allowed two nucleon states, and with this you see here we have 10 diagonal matrix elements and the following 5 off diagonal matrix elements. I have written here the off diagonal ones, the 5 off diagonal matrix elements. So the first one alpha alpha, okay, 3 by 2 3 by 2, T equal to 1, J equal to 0, again V off diagonal, okay, half half, T equal to 1, J equal to 0. Similarly I have written it over here. So in all there are how many parameters are there? 10 diagonal plus 5 off diagonal, total 15 parameters or total 15 two body matrix elements along with 2 single particle energies that we previously discussed. So total how many parameters of this 0P shell model? 17 parameters. Now once all these 17 parameters are determined, then we can say that this 0P shell model problem has been solved. Now I am not going to talk about how these are determined right now, maybe some other class. So today I have shown you various examples. In the last class I talked about general shell model procedure. Today I have shown you the various examples, various treatments. Okay, so all orbitals filled, then single particle in an orbital, next single hole in an orbital, next particle hole combination in an orbital, after that 2 particles in an orbital, right? And finally we tried to solve the 0P shell model where for the first time we have considered the residual interaction and also we have done the perturbation treatment. These two body matrix elements are a result of the perturbation treatment. I am now showing you the basics of perturbation treatment, right? Perturbation theory you have to use if you have to solve this residual interaction problem. I have written here for the perturbation treatment what are the relevant matrix elements. I have written it over here, and this is all based on the allowed two nucleon states.